This video follows on from the three-phase machine modelling video that went up a few weeks ago, and it's about a single-phase to three-phase converter, which is run off a sine wave PWM setup. So this is all in Simulink, and I'll do a SPICE implementation at some later time. So we have two converters. One is a H bridge, one is a three-phase 6-bridge, and we have some arrangement where I can look at some graphs, and I've just tucked those into a subsystem. There's a DC link, which is just a cap and some graphs, and then I've got my three-phase machine, which is the same more or less as I had in the video on the three-phase machine, and there's an end card on this video which takes you to that one if you need to see it. And then I've got myself a single-phase source, and I've got gate drive set up. I purposely haven't used the Simulink block for a PWM driver. I've knocked one up myself just to show how it can be done. In practice you probably would use the one that's actually built in, but it's nice to know how you might do it if you needed to, or if you had some special situation. And then we've got a bit of control going on here, which we'll talk about in a bit. So if we have a quick look at the machine to start off with, we have our induction machine block set, and I've got machine parameters. And I said in the video for the induction machine that you would probably take these out of your workspace by reading them. I still haven't done that because I don't intend to change this. This design is for a particular thing that I've got in mind. It's for me, so it's not for a client, so I can tell you all about it freely. And I happen to know the parameters of the machine because I have the specifications from when I bought it. So a three-phase machine of the usual kind. It's a squirrel cage induction machine with probably 8 degrees skew. I don't know for sure because I haven't seen inside, but that's the usual method. And if you've been through the modelling in the other video, you'll know that I can see the torque and the speed and fluxes and so on and so forth. And I have an idea about what the load torque will be under some nominal situation. Although in this video the load torque will be 5 Newton meters only. I'm not really looking at the dynamics as such. I'm really looking at the startup just as a mechanism of showing what the dynamics might be. But there's a range of situations that the machine might find itself in, and it isn't practical for me to model them all, or even to try to model them in great detail, because it's a process that involves a person interacting with the rotating machinery. Consequently, we don't know for sure what the loading will be. It depends what the operator of the machine actually does. I've worked it up so that we can look at the turn-on of the whole system from nothing. It would be easier to set up the link so that the link capacitor was pre-charged, and you can do that by setting an initial condition. In this case, I will be charging up to show what happens and how the converter actually starts, and some of the problems that that's involved with. All this block does is set the mean, and then I can look at some values. I pre-ran this. I wanted to see some nice looking graphs, so there's quite a small time step involved. Probably doesn't need to be that small, but I want to see that it looks really nice if I say it's a sine wave. I don't want you to have to take my word for it. It should look like a sine wave. So I ran this, and it took about 10 minutes while I was doing something else. So hopefully all the data is there, otherwise I have to re-record the video. So we've got the induction machine, we have the link, we've got a 6-switch inverter, and this is 1 half bridge, 1 half bridge, 1 half bridge, 3 phases. We measure the currents and take those off as a bus, and we can have a look at the gate drives as well if we want to. So these are with the switching signals. I've also got an enable hooked in so that I can shut off this inverter if I need to, and since we are going for startup, I need to not be trying to drive the machine when the link voltage is too low, because I'll end up taking energy from the link and there won't be, the link voltage will never rise, and nothing will really happen. I just have a lot of resistive losses. So if we have a look inside, I've got two straight MOSFETs. There's nothing special about these. You could, in principle, run this all through SimScape if you wanted to. I haven't, principally because I'm not really too worried about the characteristics of these devices. I know that this simulation isn't that accurate, but it's okay. I know it's good enough for the sort of thing that I'm trying to get out of it. If I needed more accuracy, we'd use better models, or I'd move to a different modelling platform if I thought that was wise. Or we'd build it on the bench and see what the universe makes of it. So these MOSFETs are just an RDS on and a diode as well, and a snub resistor. There's not much non-linearity involved. If we had a lot of non-linearity and we were solving the drain current expression as a square of the VGS times some parameters to do with the structure of the device, physical dimensions of the device and the doping densities, then the solver's going to have to do a lot more work. And I'm really looking at a system model at the moment, not a model which is going to give me a very plausible circuit waveforms. So I have my drive and my switch on, and this just allows me to set up whether the gate driver is a 1 or a 0 based on my enable pin. And we can look at the gate drives for the individual half bridges. And I can pull out the currents and voltages. All that happens in here is I hook certain things together in a way that allows me to get a set of currents and a set of voltages. There's nothing magical going on there. Link plus, link minus, I think that's pretty much it. So each one of these is the same. They're just a copy of each other, and the link comes in here, and I can look at my various phase currents and voltages, and this is where the machine is actually hooked up. You can tell that this is a connection over which some physical laws are enforced, because it's a different shape to the signals. If you can hear stomach grumbling noises in the background of this video, my dog is to my left, and he's picked up something off the ground this morning, and well, I shall look forward to clearing it up later anyway. I don't think he's too happy. So we have some set up for looking at the phase voltage and phase current for the three phases, and I can look at them all together as well. So this is just to hide the graphs off the main screen. If I zoom out a bit, you might be able to see it a bit better. This is the link. That's where I'm keeping my graphs. This is my 3-phase 6 switch. That's my machine. I know that somewhere down here there's my face, and that on my screen I can't see this. So if I run over there and you can't see what I'm talking about, I'm sorry for that. We have the H bridge. So this is the same two of the half bridges that are used in the 3-phase 6 switch module. It's the same thing here. They're absolutely identical, no difference. And I can look at the gate drives, and I've got enable and all the rest of it, same as before. And I've got a set of graphs as well, which allow me to look at the various currents and voltages. I've set up, we'll have a look at the carrier now, 3 sine waves. If we were building this actually building it, we'd have some embedded system that would allow us to develop the gate drive signals and to generate the sine wave that we would expect to pass to our 3-phase inverter. It might not necessarily be a sine wave. There's no reason why you couldn't do this as a space vector pulse width modulation approach, and you'd get slightly better link utilization. In fact, your link utilization would be about 14% better, probably, roughly speaking. As it is, I've got sine wave PWM both times because it allows me to reuse the PWM generation block without having to do too much extra work. But in principle, there's no reason why you couldn't do sine wave on the input side in order that you develop sine wave currents and voltages in the power network, and run your induction machine, or it doesn't have to be induction, PM machine, whatever you want, using a 6-switch space vector arrangement. But as it is here, this is my carrier generation. So all I'm doing in the carrier generation is I've got my triangle, and I've got a current demand signal, and I'm comparing the two by effectively summing or subtracting one from the other, and then I'm comparing the result of that to catch it zero crossing. And if these are all greater than equal, less than equal 0, greater than equal 0, and so forth, I have no dead time. So this 0.01, which is in each of these boxes, forces the system to have a little bit of dead time, and then I need to convert from this will be probably a double or a single precision float. No, it won't, pardon me. This will be a bool, and I'll convert it to double in order that I can run it into the gate system. So that's the method for that one. You could just use a standard Simulink block here, but effectively that's what the Simulink block does, more or less. To set up how I'm turning on the various bits of the system, I've got some clocks and a 1 and 0, and if the clock is greater than a second, I will switch on my H-bridge, which will allow the active rectifier to kick off, and at 1.5 seconds I will switch on the 6-switch inverter, which will start to run the 3-phase machine. Importantly, I've also set up the load torque on the 3-phase machine to come in at the same time that the 6-switch inverter kicks in. The reason for that is if you run this up from 0, your induction machine starts rotating backwards and you start generating electricity from the mechanical energy that you're putting in, because the load torque can be positive or negative, and we don't really have an easy method to explain to the simulator that there is no load torque unless the spindle is actually spinning. So we have a mechanism which is a bit dirty to put the load torque on when we expect the induction machine to start rotating. Other than that, I think that's more or less the setup we have. Oh yes, we didn't talk about the voltage source. So this is the power network. We have AC signal, which is in the UK 340 peak at 50 Hz. In the US it's obviously different in other places as well. And we have some inductance, and this is an inductance that is put there on purpose by the designer, in addition to any inductance that you have in the cabling to get the supply to wherever you're going to plug your inverter in. So this actually lives inside the power electronic system, and you have to rate it accordingly. So it's actually quite a large magnetic component, and it effectively it acts as a kind of a filter along with the impedance that it sees looking into the active rectifier. So, oh yes, a couple of other things. This H-bridge drive generation is principally the same as outlined in the 3-phase signal drive generation. The only difference is there's less of it. And I've done some scaling as well. So when I want to look at the currents, which we'll look at on this graph, we just have to bear in mind that I scaled the current by 10 on one of the plots in order that I can look at it in comparison with the voltage, because the point of the active rectifier is to allow us to do some power factor correction. And the way we'll know our power factor correction is working is if our currents, sine wave input currents and voltages are in phase with each other, and if they're not, then we know that our power factor correction is not working. So you need to be able to look at the currents and voltages on the same graph and compare their zero crossing points. You can compare their peaks as well, but actually it's better to compare where the rate of change is highest, because then you get the more accurate view of the comparison. Other key thing that's run up here is how the active power factor correction is achieved. So we set up a demand value for the link voltage, and because I'm not modulating 100% on my generation here, the method I'm not modulating 100% is the size of the triangle, the amplitude of the triangle and the amplitude of the current demand are not quite the same. I've done that so I don't risk over modulating and end up having switches on for an extended period, An extended period, I mean more than a couple of microseconds than they should be. I've done that so that you don't get distortion in the sine wave currents that are being drawn out of the supply. In practice, you want to try to get your modulation as close to the limit as you can without entering overmodulation. But that consequence of taking that slight care is that we need a slightly higher link voltage because our link utilization is slightly worse than it otherwise would be. And I've, by a little bit of tinkering, found that 515 volt link is about right to develop the peak currents in the three-phase machine that I wanted to. You don't need all of this system set up to do that. You can figure it out from only parts of the simulation. The actual control strategy is have a little look at the link voltage, which is developed from the link down here up to here and subtracted from our link demand value, and this will give us a constant, well it's not constant, but it is not a sine wave, it's a slowly varying value, which is the error between the link we want and the link we've currently got, link voltage we've currently got, and that'll end up in our control parameters graph. Then we have PI, and the control, both the controllers have a reset which is attached to the switching on of the active rectifier. The reason that's necessary is the control will wander off to some extent if we run it from the very beginning, where we've got uncontrolled rectification in the bridge, age bridge. Consequence of that is it doesn't come back in a reasonable amount of time. If you are doing this properly on the bench, then your embedded system would know when to switch on your active rectifier by having a little look at what your link voltage is and seeing if it had reached some threshold, and we will talk about that when we look at the graphs. So I haven't really bothered to tune these PI controllers too much. I just let them go and see how we get on, and the dynamics aren't too bad, so good enough for a video. You can tune them if you want by the usual methods, and you can Google that if you like. Not really a control tutorial, this is more discussion of the parametric simulation. So we have a PI controller which is looking at the difference between the link we want and the link we've got, and it produces a demand output which we then multiply by the input phase voltage divided by some suitable factor. The division by some suitable factor is to arrange it so that the numbers are practical. If we don't divide through, then our current demand is very large and our loop is quite unstable. So we need to either tune our controllers differently or adjust some scaling factor in to make it so that our current demand values are within a range that's plausible. It's a bit of a fudge, but in practice there will be some normalization and scaling inside your embedded system anyway to give you firstly the 2's complement if you're using it, and then you'll have to scale according to your A to D setup. So there will be some scaling in practice anyway. So we've now got a sine wave multiplied by the error in our link driving this PI, so with the output of the PI. So effectively, over a long time, it's the integrator which is in control of what's going on in terms of what's happening to this signal. So we've got a signal which is either rising or falling depending if the link is too high or too low compared to what we want, multiplied by a sine wave. So we've got a sine wave of varying amplitude, in other words amplitude modulates sine wave. And we run that into a subtractor which deals with our current. So here we've got a voltage, is it a voltage? It's a signal, which is probably a voltage in practice, but in Simulink it's a signal, which is proportional to the error, the integrated error in the link voltage, and we are subtract from that the current. So the current and the voltage will be linked to each other by virtue of the fact we want them to be in phase. So as we subtract these two, given that this one, the current, is also a sine wave, should be, we hope, we're trying to develop sine wave voltage and sine wave current. So we're effectively subtracting two sine waves. And we can call this one current demand, even though it's really an integrated voltage error. We subtract the two sine waves from each other and we have something which drives the PI, second PI controller. So this is effectively a current loop controller and this is effectively a voltage loop controller. This will give rise to our current demand, a number which is compared with the triangle to determine how what the on and off times for the various gate signals are. So the thing that allows us to do the active PFC is really how we deal with generating the voltage and current control waveforms. If we didn't use the voltage and input current in this subtraction to drive a control loop, we couldn't guarantee they were in phase. When the control loop is still acting and it's not in a state of not quiescence but steady state, if you like, there will still be some error, and that error will be driven out by the control action. But the key thing that allows us to get the voltage and the current in phase is the mechanism around here where we use them both as something to derive an error. This is effectively an error between the phase of the voltage and the current. There also the amplitude is involved, but the amplitude I can tune out by fudge factors like that one. So that's principally the method. I think we have discussed every part now. We can have a look at some data. So we'll start off having a look. I guess we'll start at the output. We'll have a look at the three-phase machine, speed and torque. There we go. Wow, that took a long time. Obviously, there's quite a lot of data in these graphs at the moment, or stored in the background rather, so it's taken a little while for things to come up. So, first thing is 1.5 seconds of nothing, because the machine is not involved in the simulation. There's no load torque applied because there's a switch and a clock, and the three-phase inverter is not running because even though the gate drive signals are applied to it, my enable line is shut off. So there's initially large currents in this is the ABC frame, reference frame of the machine. So this is what we measure on this data. And if we had the capacity to measure the rotor current in the rotor bars, we ought to see this waveform, or we hope we would anyway. A speed ramp up from nothing to just below the synchronous speed. The synchronous is 1500, and the machine is somewhat loaded, so we're just a bit below that, probably about 1430, 1450 I guess. And we can have a look at the electrical angle which the rotor shaft has turned through. So the fact that this keeps on increasing, and I just limit it at 2 pi, is a good thing. It means it's spinning in one direction, and it's not. If we had this go negative, it means the machine has stalled and then gone backwards. And after a bit of spinning up period, the machine currents become much more sinusoidal, and we should find them looking quite nice if we can get a couple of cycles up. That's pretty good. It's pretty much a sine wave, a little bit depression on the top maybe, and the bottom, and they look like they're 120 degrees out of phase to me. So the machine is spinning. I will not look at the torque because the graphs are taking forever to load because of the amount of data I put in them. We can have a little look at let's have a look at the control parameters. Then we'll have a look at the line side. I don't think it would do much good to put up graphs showing the PWM switching, because switching signals look like switching signals. Unless you're really zoomed in, you can't tell much. So we've got a value of VD error. So this is the the error between the link we'd like to have, which is 515, and the link that we've got, which is whatever we've managed to charge the link capacitor up to. And there's a period here, which we'll see in another graph, where we have uncontrolled rectification. In fact, we have uncontrolled rectification up to a second. The uncontrolled rectification is the body diode, the MOSFETs, essentially acting like a full bridge rectifier, uncontrolled rectifier, as you might find in a linear power supply from, well, linear power supply is still very useful for low noise situations, that sort of thing, but they're not very efficient, they're quite heavy. So I should say linear power supplies of times past, but actually I'm a big fan of linear power supplies, so they're still around. But in the standard linear power supply, it's uncontrolled rectification into usually a capacitive energy storage. And that's what we observe here, and the 515 minus about 200 leads us to about 300 and something, and 300 and something is the peak of the line voltage in the UK, and that's how that comes into being. Then we have a period of, it always does this to me, every video. I think it does it just to embarrass me. Go away. We have a period of active rectification between a second and 1.5 seconds, where the gate drive of the H bridge is set to enabled, and it fires in such a way as to charge up the link via the MOSFET body, the MOSFET channel, and the body diode is not really involved because the peak voltage of the sine wave, which is applied to the midpoint between the two MOSFETs in the half bridge, and the link that we're trying to drive up to is not appropriate to switch on the body diode, so it has to be active rectification. We'll find some pretty large currents in this region. They are not practically realistic, but for the limitations of this simulation they're okay. There's quite a lot of things that are missing, like bus bar resistances, and you could, if you wanted to, adjust the way your gate drive signals are developed to have some active current limiting when you have your active rectifier operating to drive up the link voltage when you're going to switch on, and that would be the common practice. But it's not included here because I don't want to spend too much time developing a gate drive signal just to perfect a simulation which in reality is not going to match what I get on the bench anyway. It'll be close, but not the same. 1.5 seconds we'll switch on the machine, and we just had a look at the machine signals and we can see that there was a ramping up of the speed and the currents and so forth. If we look at the voltage loop PID output, so we're now looking at this node here. So this is what the integrator and the proportional error are getting up to. They are large in the beginning, and then there's this downward trend as this drops in because our link voltage is rising due to our uncontrolled rectifier, and then it sort of goes up because the uncontrolled rectifier can't drag the link up far enough, and then there's this sudden discontinuity. This discontinuity exists here because this is when the reset happens. So all the control that happens before here really doesn't have much bearing on how the system acts, and we can pretty much ignore it. What we are interested in is the error here is about 200, and 320 something or 330 something minus 515 is about 200 or so. So that's how that error point comes into being, and the spikiness of this is due to the sine wave nature of the input signal, voltage signal. A current demand loop is taken from just here. So this is the multiplication of our integrated voltage error with our signal, which is proportional to the size of the input voltage and has its phase information as well. So we should expect sine wave, and we get it. And since we're driving the link up in voltage because active rectifier is charging the link capacitor, we find the error is getting smaller, so the overall successive amplitude of each peak is lower until we reach the point where we don't need to charge the link up anymore, where we've got no error in our, or very little error. In fact, it slightly overcharges the link, but never mind. When we add the induction machine on, that quickly gets the link back to the right spot. So the currents in our single phase side, that's the active rectifier side, we've got some uncontrolled rectification. This is actually measured in amps. So these currents are pretty enormous, and if you were plugging this into a 32 amp circuit in a light commercial setting, or even a domestic setting, pulling 200 amps won't go that well for you. So you need to do something to limit your, you would call this inrush, although that's probably only 100. It's not best practice to do that. You should try to keep it below 30. You could do that by, if you really want to, you can just switch in a resistor, switch out a resistor with a contactor. You can't really do anything about this with the active rectifier, because the active rectifier is not involved here at the moment. The other thing you can do is slightly increase the size of the inductance, which is in the, you can slightly increase the size of that inductor. The difficulty with that is it will add a time constant to your system, which makes it more difficult for you to get a low order harmonic content in your sine wave currents drawn out of the supply, and it makes it difficult. Essentially, you're limiting your bandwidth to the point where 50 Hz is almost being cut, and you get putting in phase shifts which your system has to then take out. So you can't take it too big. Other problem, of course, is the bigger you make it, the more it'll cost, the more space it'll take up, and the bigger the inductance, usually the more copper, and the more copper, the more resistance, and the more resistance, the more I2R loss. So it's going to get hotter. So there are some pretty good reasons not to over-egg the size of that inductance more than you have to. I think I've been pretty generous in this. It's a simulator, I can be as generous as I like. But you would want to deal with that with some inrush arrangement. The active rectifier, you can control the size of these currents by controlling your gate waveforms. It's just that I haven't in this case, so we've got this enormous currents, but not the end of the world. We overcharge the link a bit, which is why they suddenly stop. But when we start to discharge the link capacitor a bit by running the 3-phase 6-switch bridge and the induction machine, we can see that there is some current drawn from the supply, the single-phase supply, in order to keep topping up the link. And we hope very much that this sine wave is a sine wave. I'll take the risk of zooming in. Sine wave-ish. Is in phase with the supply voltage. Now I have to wait for it to zoom out again. There we go. Sorry, my dog's just appeared. Coming up. Go on then. Look, it's all the people. Last thing is the SPWM drive, and there we go. This is the value which is actually sent to the gate drive signal generation, only from 1 second onwards, because it's reset before that, so this doesn't actually get to do much, anything in fact. So we should see that there is actually some stuff here. It's just very, very small on this scale. If we zoom in a bit, maybe we can see some. There you go, 1 or 2 amps only, which is our steady state current required to keep the link charged up sufficiently for us to drive the induction machine. The currents that we saw in the beginning, just after 1 second, is consistent with the very high currents that we see taken from the single phase supply to charge up the link cap. So effectively we need to charge up the link cap a bit slower and extend the period of time from 1 second to just here. And you probably wouldn't have to extend it by very much to get this current to something more reasonable. So that's the control arrangement, and we can have a look at the line side parameters. So this is in the single phase supply effectively. In this graph I've got voltage in yellow on the top and I've got current in blue, but the current in blue is multiplied by 10. It's done so that in this region here, which is the region I really care about, because this represents our steady state after all the dynamics are dealt with of the startup, the dynamics of the startup are dealt with, we can have a look and see what's happening, whether the current and voltage are in phase with each other. It does of course look very much like there's 2100 amps flowing into the... It's not, it's only 200, which is still bad, but as I said, you arrange your gate drive setup for your active rectifier in this initial region to operate as not drawing that much current. Effectively you do current limiting by limiting your switched on and switch off periods. So if we look at the turning on of the, well actually we can look here in the beginning. This is the uncontrolled rectification, and we are charging up a capacitor through some diodes effectively, just like you would in a linear power supply. And if you think back to the most fundamental courses on electronic engineering, you'll know that the current and voltage in a capacitor are out of phase by a certain arrangement, by 90 degrees in fact. And sure enough, here we have a voltage in yellow and the current times 10 in blue. So this is about just under 100 amps, 900 amps, 90 amps or so. So you'd want to limit that as well, it's too big. And they're out of phase by about 90 degrees. And when the link voltage starts to rise, we can see this not quite conduction all the time through the diodes, and there's periods of no conduction. And this sort of waveform is extremely typical of a uncontrolled rectifier, which is topping up a capacitor at the peak of the voltage waveform. Oh, I've not finished with that one yet. Back we go. Then we have period of active rectification, and you can see the leg voltage. This is the leg of the... Where am I looking? Yes. So the leg voltage is the voltage on the other side, the power electronic side of our smoothing inductor. The reason I'm calling it leg voltage, even though it's here, is the same voltage that you will find just here. And this is usually called the leg of this half bridge. So we find that the leg voltage gets up to about 320 something. I won't zoom in because it takes ages. And that is the peak of the supply voltage that I have in the UK, which I've put into the simulation. Only when the active rectifier kicks in can we take the link and therefore the leg voltage above the value of the peak of the line voltage. And if we look at the currents that are involved, they're still not in phase. This isn't that surprising. We are working the control and the H bridge quite hard to drag out all the current we can and charge up this capacitor. We are still fundamentally charging a capacitor with a voltage, and the current in the capacitor and the voltage across that's driving that current should still be out of phase if we're pushing lots of current in. Only later we can make the correction. And also the current is very non-sinusoidal, and we should expect a lot of harmonic injection into the supply. This is the switch on event. You can see everything changes. So it's not surprising that we don't have good characteristics here. And we take up the link voltage quite quickly, and then we find that the active rectifier proper starts behaving in a way we'd like it to just here. I want to talk about this region. Go away, god damn you. I want to talk about this region first, and then we'll go back and look at this, because there's something quite interesting. Not interesting. I suppose it is interesting, but something that's maybe not expected should be happening here. We've slightly overcharged the link capacitor at this point, and the controller will do something that maybe is not expected in order to try and ameliorate that. But first of all, I want to talk about the expected behavior, which is 1.5 seconds. We switch on the 6-switch inverter that's driving an induction machine, and we have a little look and see what happens with the waveform. So try to get a few of these here. These currents are not very sinusoidal, but if you look at the zero crossings, they're not that far away. It's pretty close. This is the startup transient or the dynamics for the induction machine. So fluxes are very high. There would be saturation of the magnetic material, the electrical steel. That's not shown because our model of the induction machine doesn't include any saturation. It doesn't include any thermal effects. In fact, it doesn't include quite a lot of things. So there's not much to be taken from these waveforms. They are nonlinearities that are produced here, not from the induction machine. They are from the MOSFET model, dominantly the MOSFET model. Also a little bit the control loop is probably not quite doing what we'd expect it to. We could go back and look at the control loop waveforms and see if they really are the right shape or if they're somewhat clipped at the top, but it's probably to do with our switching devices. The point is, even though we know it's wrong, it will be wrong by a number of other ways when we actually build it, so it doesn't really matter if we're happy with this shape or not, because you're not going to see it in reality. Obviously the sine wave looks okay because that's what's coming off the supply. In practice, of course, the supply in the UK is not a lovely looking sine wave. It's got some horrible harmonics in it already from all the other things that are plugged in and drawing a current from the network. So that will also act to modify our current waveforms. If we go a little bit further on to where the induction machine is running, it's up to speed and everything is in steady state, we can actually see, I don't need to zoom in, we have reasonably sinusoidal currents in phase with the sine wave. And I know it's in phase not because the peaks are lined up, the peaks are not quite lined up because there's some distortion in the current still, but because the zero crossings are all matching. So did we get our active PFC? Yeah, we did. Do we have some harmonic injection into the supply? Yes. We could deal with it. There isn't really time for discussion now, but there are mechanisms to make this look more sinusoidal. And you might want to use those, or you might decide actually I'm okay with a bit of back injection, it's alright. Depends what EMC criteria you're trying to hit and that sort of thing. So we managed to get our active PFC. This bit here, we've overcharged the link, and if you look reasonably hard, you can see that the current and the voltage are actually in antiphase with each other. This is the control loops method of attempting to discharge the link capacitor a bit by passing energy back into the supply. There's nothing to say that you couldn't use this as active braking method. If you wanted to stop the machine in a hurry from spinning, and when it's already spinning you want to stop it, you can essentially charge up your link cap by taking the mechanical energy from the machine and slowing it down, and your link cap is overcharged compared to your demand value which you set in your embedded system. Then the controller setup we have here will run the gate drive in such a way that current is passed back into the supply network. So what is the angle here where it's 180? Could you tell me the power factor? I would call the power factor 1. Other people might say it doesn't make sense to ask what is the power factor, but this is a curiosity, and it's worthwhile because if you're, I don't know, for example, say you're running two machines and you've got some mechanical to electrical to mechanical system for some reason, you can run it bidirectionally, but you will have this antiphase setup where you're passing energy in the wrong direction. Right, the dog's decided he's had enough, can't take any more. If we look at the leg voltages in this region, we'll see switching waveforms. Oh, that's why we don't like to look at switching waveforms. It's horrible. Let's try to. So you can see here is the dominantly low, here is the dominantly high, and this is somewhere in the middle. So I pick somewhere in the middle. Try and take a couple out. Okay, it's a third on, 2/3 off, roughly speaking. This is taken on the power electronic side of that inductor, which we talked about earlier. So that's our line side performance, which is believable. It's alright, not great, but it's okay. The main problems are our current's still not very sinusoidal, it's only quite sinusoidal, and we have these startup transients which are drawing out far too much current, and we're definitely going to blow a fuse or MCB or something's going to go along the line, and we have to do something to stop it. Righty, what else is there to look at? Not very much, I don't think. We could take a look at some of the current waveforms and so forth, but we've seen them really because we look down here. So you can drop me an email. Oh, we didn't look at the link. We'll have a quick look at the link. Just wait for this to load. So we've got the three-phase DC bus current, so that's negative values here are power out of the three-phase into the link. Single-phase DC bus, so it's negative here is power out of the single-phase into the link. So this is power into the system, this is power out of the system. This is the stored energy, or the currents that are going in and out of the energy storage. So negative is stored energy effectively, and positive is energy leaving the link. So here we are storing up initially. And the bottom one is the link voltage, and we can see uncontrolled rectification up to about 320, active rectifier pulls us up to 515, little bit of decay down, here kicks in induction machine, and that pulls a little bit of current out of the link, but a control system arranges it so that the link is recharged and the voltage and current which do that recharging are in phase on the line side, single phase line side, and it holds at 515 continuously. If we wanted to get the currents in this region down, we need to lengthen that out a bit more, or use and to do that we can change our gate drive setup a little bit from our embedded system in our active rectifier, or we could try to increase the size of the smoothing component inductor, or reduce the size of the stored energy capacitor, of course. But there's depends on the cost and the volume you want and the weight you've got to try and hit, the amount of heat you're allowed to dissipate, lots of factors involved, and none of those things really come into the simulation. So I think we covered everything now. If you've got any questions about this, or you want to discuss anything, feel free to drop me an email.